Good morning to my examiners, Madam Fazlita binti Muhammad Tamiri and Dr. Nazrin Adrian bin Amaluddin, and also to my supervisor, IR Dr. Muhammad Azlan bin Ismail. I am Alfera Yap, and I would like to present about my final year project with the title Simulation Analysis on the Effect of Inlet Channel Bed Slope and Diameter of Basin for Water Vortex Turbine System. Okay, so here is my presentation outline. Firstly, we will take a look on the introduction, then the literature review, methodology, result and discussion, conclusion, and lastly is the future work. So basically, my project is related to a vortex turbine system. The problem statement for this project is regarding the limited research that focus on the inlet channel and diameter of basin. So my objective here is to develop CFD modeling for the water vortex system and validate it by comparing the vortex flow simulation data with the experimental work. Then study the effects of the vortex flow for the inlet channel bed slope and diameter of basin, such as their stability and uniformity. Okay, so the policy to install the vortex systems is usually based on Asian Renewable Energy Guidelines, but this is only applicable for Peninsular Malaysia, Sabah, and Labuan. For Sarawak, they have their own guideline, which is Sarawak Energy. So according to the FIT scheme, it is not suitable enough to sell the electricity to the TNB company because the generated electricity for these micro vortex systems is usually relatively small, which is around 5 to 100 kilowatts. Okay, so regarding the vortex turbine system, the mechanical energy generator will only focus on the turbine configurations, while for the hydraulic energy generator, it will be related to the basin, outlet, and also the inlet channel. For the methodology, this project starts from figuring the problem statement, background study, then the experimental work was done in the laboratory, and the simulation was also done at the same time. After that, do the validation. If the validation is okay, then proceed to the documentation, which is the result and the discussion of this project findings. So for the experimental work, the flow rate was set to be constant, which is 34 gallons per minute, with the diffuser chose is 10 degree. Then the vortex height obtained is 0.22 meter. After I do the experimental work, then I proceed with the simulation analysis, which use SolidWorks 2018 and NCCFX R21 software. For this simulation, the water vortex height obtained is 0.24 meter, and the percentage of difference is 9.09%. So as you can see for the graph that have 4 different color, which is blue, green, yellow, and red, this is how to determine the convergence criteria. It can be seen that the graph start to become steady state after the 500th iteration, which means that the simulation is stabilized. Then after do the mesh independent analysis, the selected element size is 0.012 meter. Okay, so this is how I changed the configurations of the model. So originally the inner channel bed slope is flat, which means no slope at all, and the original diameter of the basin is 0.39 meter. Then for the first one is that I changed for the bed slope. Okay, what I changed in the bed slope is that I changed from the flat bed slope to 2, 4, and 6 degree. But the diameter I remain the same on the original size, which is 0.39 meter. Okay, then for the second objectives for the diameter of basin, this I changed the size to 0.3, 0.5, and 0.6 meter. And for this, I let the bed slope for the inner channel to be the original one, which is without bed slope, or also can say 0 degree. Okay, now let's take a look for the result that I have obtained for the inner channel bed slope. So first of all, let me briefly explain a little bit regarding the bed slope. So as you can see the picture on the top left corner, there will be 3 different zones that exist on the mud slope. As we can see the pictures obtained from the Doherty and Franzini, the flow initially accelerates from A to C and uniform at the middle part and decelerate from D to E. Then when it is beyond the E point, new depth of uniform flow was achieved. This is the phenomenon occur inside the channel with the bed slope. So at first I expect that the water flow will accelerate when it went from upstream to downstream. So when it accelerates, it will increase the water flow velocity and then increase the water vortex height. But then there are no effect on the vortex height. As you can see on the graph plotted, all the vortex height are almost similar for all different bed slope. So what I can say is that this might be because of the continuous water flow, which level up the volume of the water until it reached at one constant volume. This is related to the volume flow rate, where the volume flow rate in and out is equal. Although there is a change for the inlet channel cross-sectional area from wider to narrower with the mild slope. So after I do all the simulation by changing different bed slope, I found out that it actually doesn't affect the water flow or the vortex height. And from the second data that I observed after the water vortex profile formation, which is the water superficial velocity, the red contour indicates the water flow that enter from the inlet channel, while the blue one is another side of the basin. And the graph was plotted as shown below. So from this data, it is actually opposite. What I mean is that the left side of the graph indicates the red contour, and for the right side of the graph indicates the blue contour. But the point is that both sides shows almost symmetry velocity distribution, which is around 1 meter per second for all different bed slope. Just that the blue contour shows slightly higher peak velocity than the red contour. Okay, so for the inlet channel, inlet geometry velocity, this I measured throughout the inlet channel just to identify the velocity changes that occur inside the channel. When I plotted it for all different bed slope, I found out that the velocity actually does increase as the inlet channel bed slope is increased, just as what I expected to happen. But then when it flows from the initial of the inlet channel to the end of the inlet channel, the velocity is actually converged to almost similar velocity, which is around 0.3 meter per second. So in my opinion, this might be related to the volume flow rate that I mentioned earlier. Okay, so for the streamline, all the results shows almost similar for all different bed slope, and all are well distributed inside the basin. Still, there are no changes for this. Okay, now moving on to the diameter of the basin results. So for this study, changes occur as the diameter of the basin was changed. Okay, if we see through the water vortex profile formation, the flow transitions inside the basin is gradually changed from an isosurface with slightly jump between the inlet channel and basin and slowly becomes smoother isosurface as the diameter of the basin getting larger. So this happened because the larger the diameter of the basin, the greater the time that the water have to flow inside the basin, which stabilize the water surface. So when it is plotted to a graph, the highest vortex height is 0.39 meter of basin, so which is the original size of basin. Okay, so in terms of the vortex height, 0.39 meter is the preferable results because it has the highest vortex height. So the aim is that the higher the vortex height, the higher the strength of the vortex that form inside the basin. Okay, so for the water superficial velocity data, there are changes in terms of the velocity. For the diameter of the basin, 0.3 meter, it shows relatively slow velocity distribution and not symmetry and well distributed. Okay, so for 0.39 meter, it shows well distribution and higher velocity compared to the others. Then for the 0.5 meter, the velocity are not well distributed. And lastly, for 0.6, it shows imbalanced velocity where the red contour velocity is much slower than the blue contour that has much faster velocity. So for the data, it can also be seen that the peak velocity for 0.3, 0.39, 0.5 give almost the same peak velocity, which is almost 1 meter per second. But for the 0.6 meter, it only reached until about 0.8 meter per second, which is much slower. And the right side of the basin velocity is getting slower, while the left side velocity is getting faster. So this described for the 0.6 meter basin. And this shows that the velocity is imbalanced for both sides, which is very not preferable. So it can be concluded that the preferable diameter for this data is 0.39 meter because it has balanced velocity flow, well distributed, and the velocity is quite higher than the others. Moving on to the streamline data, it can be seen that the diameter of the basin with 0.3 meter shows more uniform distribution of streamline in the domain compared to the others. And the 0.6 meter shows that there is imaginary wall exists. So this imaginary wall is actually a stagnation of water flow that can be occurred along the wall of the basin. This means that the water flow near the wall of the basin has relatively extremely small movement of fluid, which is almost not moving. So this phenomenon can be related to the free vortex flow that flows the relation between the tangential velocity, which are inversely proportional to the radius. The larger the diameter of the basin, the larger the radius, and the slower the tangential velocity will be, which cause this stagnation to occur. So considering the uniform distribution and well distributed of the water flow, the 0.3 meter basin is the preferable one. So from these research findings, it can be wrapped up that the change made for the inlet channel configuration where the bed slope was added actually does not affect or give any changes for the vortex height or the water surface formation. The only changes that can be observed is the velocity throughout the inlet channel from the initial to the end of the inlet channel. But still, the velocity will end up almost similar velocity as it reached to the basin. So still, there's no changes occur. For the diameter of the basin, each of the data representation gives different preferable data. All of these preferable data consider the smooth water transitions, high water vortex, uniform, and well-distributed velocity. So, as a conclusion for my final year project, I have achieved my objectives where I successfully utilized the use of CFD simulation, analysis, and validate it with 9.09%, which is quite acceptable considering slightly difference from the experimental work and the simulation analysis. Then, I also achieved my second and third objectives, where I want to investigate the effects or changes that occur when I change the parameter configurations. So from the result obtained, only the diameter of the basin that have effects, and the inlet channel bed slope does not have any changes in all of the results obtained. Okay, so basically my project does not come out with one optimum parameter for the inlet channel and the diameter of the basin. I'm here just to investigate the effects of the water vortex flow, including the characteristics, the behavior, and the changes. Okay, last but not least is regarding the future work recommendations. So I would like to recommend the placement of the turbine inside the basin with this study that related to the inlet channel and the diameter of the basin. I believe it will affect the data, and I would also recommend to utilize CAD and CFD again to study the vortex system rather than directly fabricate it. These simulations can be said almost reliable, so it is better to do the simulation first until it meets the desirable data before we fabricate it. So this is to save our time and cost. So that's all from me. Thank you for your patience in listening to my Viva presentation.